In this lab, we observed an object moving with a constant velocity. Newton's second law states that net force is equal to change in momentum over change in time. Since our object moved with a constant velocity, there was no change in momentum, and therefore there was no net force acting on the object. So here we see Newton's second law with a little picture demonstrating it. And here's the form we learned, where F equals change in momentum over change in time. F is also equal to mass times acceleration, which is just the same equation but rearranged. So in our lab, what we did was we had something move with a constant velocity, therefore the acceleration was 0, and we assumed that the net force acting on the object is also 0 since the mass is kept constant. So using stuff like tracker, which is what we used in this lab, and computational models is very important in real life because we can track the motion of objects or anything else in a very effective way without having to do it by hand. So a computer can do it for us. So in this lab, I analyzed the motion of a tennis ball rolling across the ground. So here's my video. The video was 0.467 seconds long and it was around 15 frames. So Tracker made a graph of position versus time for this object as well as all the data over here. And it graphed it. So we can see it's a straight line since the velocity was constant and there was no net force acting on it. And if we wanted to find the velocity, we could also take the slope of this line right here. I also chose to have the axes with the positive x-axis on the right and the negative x-axis on the left, and with the ball starting right at 0, 0, and then the positive y-axis on top and the negative y-axis on the bottom. So then I went over here into Glowscript and made a computational model of this. So there were several sections I had to fill in, such as the ball's mass, which was 0.0577 kilograms, the ball's initial position, which was 0, 0, 0, and the ball's initial velocity, 0.58200. And I calculated this initial velocity by looking at the first 2 frames and doing the change in position over the change in time. Then I had to edit several more things, such as the initial time, which was 0, and the delta t, which is 0.01, because this is what's going to go into the loop down here, and we want to make this number small so that we get more accurate data and more accurate graphing of this data. So I set the time to be less than 0.467 seconds because that's how long my video was. And then I made sure, this part was important, to make the F net equal to 0, 0, 0, since the net force on the ball was supposed to be 0. Then the ball's velocity was the initial velocity plus F net divided by mass times delta t. And in this situation, F net is 0, so the ball's velocity stays constant. Then the ball's position was the initial position plus the ball's velocity times delta t. So the ball's position was changing by a constant rate since the velocity was constant, as well as the delta t. And then all we had to do was run this program. Here is a video of the ball rolling to the right, and here's a graph of position versus time and velocity versus time. We can see that the velocity versus time graph is a straight line since the velocity is constant, and then the position versus time has a constant positive slope, which is equivalent to something around 0.528 meters per second. And here is the data down here that Glowscript was able to find. Then what I did was I compared my model versus my experiment. So I put all of my data here on the left, and then I have my graph of the data over here with position on the y-axis and time on the x-axis. The experimental data is in blue over here, and then the model data is in red, so we can see they match pretty closely. The experimental data does go a little bit lower than the model at the end, and this is likely because the ball did slow down at the end, so its velocity slowed down a little bit. Now, there are several issues that we need to talk about. For the tracker, if I wanted to flip the axes, and I decided to have the negative x-axis over here and the positive x-axis over here, the graph would look pretty similar. It's just it would start at 0 right here for the position and then go downhill, but the line would still be straight since the ball would still be moving in with constant velocity. If I flip the y-axis, it would have no difference since the ball isn't moving at all in the y direction. So in my video, if we could play it one more time, before the video starts, I actually had to push the ball, so accelerated at first. But during the video, we assumed that it was moving with a constant velocity and with no air resistance, since there is no net force. We can also assume that the gravitational force going down and then normal forces going up cancel out since there is no movement in the y direction. However, we can't really tell how many pushes and pulls are going on here because even though it's very close to a constant velocity, the model isn't perfect and doesn't perfectly align with the computational model we made in Glowscript. So this was my Physics Lab 1. Thank you.